Okay, it's 9:30. You are attending the Computing in the Network Research Group, and welcome wherever you are, whatever time zone, morning, afternoon, evening. I appreciate all of you who are here in the room because this is the first time that I've attended an IETF in 3 years, so it's the first time I've used a lot of these tools in person, so this is great. And I have my co-chairs online, Jemfe or Jeffrey, and Marie-José. He's calling in from China, and Marie-José from Montreal, Canada. So we've got the globe covered, or parts of it. Let's get started. This is just a reminder that the IETF has a whole collection of policies that actually in recent versions of slides, we have been told that we should really note these very well, that there are various topics regarding patents and code of conduct in particular that are really important. And by participating in the IETF, you agree to follow all these processes and policies. One that is very sensitive, of course, is whether or not your IETF contributions or IRTF contributions are covered by patents, and that we like to hear about that early and often. As a participant, if you are participating with audio and video, implicitly, all of that is made public, and you give your consent by participating here. We try to observe privacy policies, and I think most importantly, we really want to create a respectful environment where people are treated respectfully and thoughtfully and recognize that there's a really diverse audience of participants. And if anything should arise where you feel harassed or you notice that someone else is being harassed, there is an ombudsman and process for handling that. And please do not hesitate to approach working group chairs as well, should you need an intermediary for that. These are the places where many of those policies reside, should you seek to have more detailed understanding of them. Everything from working group processes, I've already mentioned several of these, but also copyright as well. For those of you who are here, you made it here. For those of you online, you've also made it here. But please note, if you do not already have the Meet Echo tool on your computer or personal, your phone, please do so, even if you're in the room, because that's how we automatically know that you're here. The blue sheets are now integrated. There's also integrated chat into the tool, and we will try to monitor both the chat and the queue for questions. So in-person participants, please use the tool also not only to sign in, but to join the mic queue. And for remote participants, please have your audio and video muted unless you're speaking, and headphones are recommended. We would love a note taker. Is there anybody who'd like to jump in? It's a shared tool, so should you feel inspired, you can always join in. But is there somebody who would like to take that role officially? If not, we will go back and insert minutes while reviewing the video. This is the mailing list. Please join. We welcome your inputs. And all meeting materials are online, and all the slides have been uploaded. Please note that there is a difference between the goals of the IETF and the goals of the IRTF, that the research task force is really focused on longer term research issues, and it is not about standardizations and specifications per se, which is really in the province of the IETF. And so you'll see that the drafts that we have produced, at least at this point in time, are all informational drafts. There is also a wonderful primer for IRTF culture, and for those attending the broader IETF. Today we have a full agenda, so we're going to try to stick to the timeline very strictly, so please do not take it personally. If we say your time is up, one of us will try to keep you posted if you're running long. But the the way we're going to run things today are that Marie-Josée, one of the co-chairs, will revisit COIN and advances that have happened in the last few years since the working group began a little before COVID. And then we're going to switch gears and have a couple of research presentations. I believe the first one is Orchestra, and Jörg Ott will be presenting. This is a paper that appeared in Usenix. What was it? Okay. And then secondly, we'll have the Share Nothing Edge AI presentation. We're going to then shift gears into some of the research drafts. We have, last time we heard about the use cases. This time we will hear about the analysis of overarching issues that cut across all the use cases. At the moment, its title is use case analysis, but there'll be some discussion about what it actually should be called. We will also have a brief overview of where we stand with the terminology draft. Then we will have a couple of individual contributions that have not as yet been adopted by the research group, but are interesting, quite interesting. And we welcome your discussion. And then what next? We have quite a few documents. You can see that we have, actually, if you go to the data tracker, the first three are documents that have actually been adopted by the working group, and there has been some discussion about adopting the directions for computing in the network draft as well, but that will be a topic for discussion as well today. But that will be the focus of the drafts. We have quite a few other related drafts. Again, if you go to the data tracker, some non-expired drafts that have been contributed that still exist as individual IDs. We have quite a collection of expired drafts, and again, in the final part of our discussions today, we can have we can review what our policy should be going forward, whether these drafts should simply remain expired or whether we should resurrect some of these and make them current. Without further ado, we're actually ahead. We have a couple of extra moments. So I think I'm going to switch gears and allow Marie-Josée to begin her presentation. I'm going to stop sharing. And Marie-Josée, would you like to drive from your side or? Okay, you're going to take it from there. We cannot hear you as yet.
Yes, I know I had to give Mexico the right to hear me. Okay, so I'm doing this as some kind of a dual hat, as both the co-chair of this research group, but also as somebody who's been working a lot in COIN and related research in the past 4 years. And I think it's important to see how the landscape has changed, and quite dramatically to a certain extent. When we started this group, we had, of course, the Tofino switches, which was, I call it the shiny object, which was essentially telling us that there was a way to modify packets while they were in transit in the network, and that we could, think of all kinds of interesting things that we could do with this. And of course, it was related to a language that was used to program these switches, P4. And since then, there's a lot of, I think, data-driven and computing-driven approaches that have appeared that have nothing to do with Tofino. And when Tofino also was kind of put on the sideline by Intel, somebody told me, well, COIN is dead. Well, actually not, because I think in the 4 years that led to almost this Tofino being pushed a little bit aside, a lot of us were asked, what is computing in the network? What is the difference between computing in the network and edge computing and everything else that's data-driven in the system? And I think I want this presentation, which is way too long, And I think I'm just going to go through some. Yeah, I know you're smiling. I looked at it this morning, and I usually tell my grad students, no, if you have a half an hour, don't make more than 5 or 10 slides, and I have 18, and they're very full. But I will go through them. But I think I want this to be some kind of a stake in the ground and say, this is what happened. I'm going to just maybe glance over a number of things, but I think the title says it. In the last 4 years, what we had an incredible rise in programmable devices, distributed systems, and the incredible rise of AI everywhere in the network, and also how the network can help AI, and obviously digital twins. So these things don't happen in a vacuum. And I want to thank 3 people who have been very useful for me in putting these ideas together and making sure that it was all aligned. David Clark, who's always been my mentor. François-Xavier de Veilly, who was at Mila here, which is probably the most important AI group in Montreal, but also in the world. And there was Zilberman, who was there at the beginning of this group, but also has been continuously supporting us. And yes, I know I don't have a lot of time. So the big thing about this slide is 5G is, past right now, and 6G is there. Nobody really knows what 6G is, but what has been happening in 6G about a month ago, maybe 2, I was invited to a 6G meeting online organized by Capgemini, and everybody from Nokia, from University College London, from everybody was saying, okay, it's edge fog and cloud. There's a lot of machine learning, a lot of artificial intelligence, and essentially what we're talking about is not just the Internet of Things. It's almost the Internet of everything. Everything's connected. And what can programmability bring to that? Because a lot of people also brought it up. There's also this next G. I call it the next G. It's this network of network. And this is the big discussion that I had with Dave was, it's a system of system. It's a network of network. This is actually what the Internet was. It was a distributed system. And the pendulum is moving, from this hyper-centralization, which is also because of regional autonomy, because of data governance. There's a lot of autonomous and federated systems that basically need to work without connectivity to the cloud. Obviously, energy saving, and I know this is sustainability is a big thing for Eve. And so, like the people are going to say probably later today, distributed systems are more suitable for these multidisciplinary application. And for COIN, what does it mean for COIN is that there is a lot of things we can do when we have computing for AI in the network and the network for AI. We need to have modeling and digital twins. Where do we get that? From the data that is being gathered inside the network. We have programmable networks already, not just switches, but NICs and all kinds of CPU and GPU and IPUs. And we have the rise of intelligent network nodes, which are like these little entities that can do a lot of things on their own autonomously if they're in a car or an autonomous vehicle, but also could be doing things if they're in a RAN, can do things with the other RANs around them. So I want to talk a little bit about each of these things. And yes, I am very careful with the time. So this is actually how the whole thing fits together. I could spend probably half a semester just talking about this, but we're here. We're actually, in effect, an intelligent or an artificial intelligence Internet of Things. And so we're related to what? Green networking, because we want to know how much kilowatt hour we're taking. We're related to applications because we have KPIs. And, because we do functional decomposition and modeling. And these are the axes that I just described. And all of these things are not independent. They are related. They all need to have some form of CPU, of some form of programmable device inside a network to work. And I hope that, and this is actually what COIN's about. What can we do when we can have things that compute inside the network? So essentially what we want is distributing the functionality. And I don't want to take over the next presentation this afternoon, but functionally we want to have what I call always for my students, the life of a packet. What happens, I always tell my students, if you want to know where to put computing in the network, think of what happens from a packet. The minute it leaves your user device or even your home router, all the way to the cloud. A lot of people think this is a one hop. No, actually, there's a number of hops there. So how do we do that? How do we make sure that we can actually see where that packet is going throughout each layer in the network? There's also the vertical, is this distribute decisions to improve overall efficiencies. And that I will talk a little bit about twins and multi-scale AI and machine learning. But we have also to think, what can we do with computing in the network, working on the data, that can help the network work better, being more reliable and being better suitable for like the IoT. Oh, and I have a typo. There shouldn't be a parenthesis here. And IoT, I think, is driving a lot of this thing, because now there's programmable devices everywhere. And we know that IoT works with container and orchestration with R. Oh my God, I think I read these things 100 times and I still find typos. Anyway, and we need them to know how to resource share. And resource share in that case is not just sharing information, but made aware of what happens with the power, with the bandwidth, with the access to the cloud. Maybe I cannot access the cloud, but my neighbor can. And maybe I can actually then establish some kind of connectivity. Programmable knows why, and this is us, COIN. Enhanced data management. I know that data has been quite a discussion in this group since the beginning, but we need to do load management. We need maybe to do compression. Maybe we need data reduction. Actually, the people from AI can give us a lot of hints there, because they are used to send all their training data to the cloud, but that's offline. And for the real-time operations, they do things wherever the information is needed. And I would like it for this group to be known that this is not only at the edge. This is everywhere where we can actually act on that data. It can be an aggregation point in everywhere in what I call the cloud edge continuum. So this is COIN. This is very much what COIN can do. And of course, there's this security thing, and I'm not a security expert, but there's going to be a presentation on security later in this session. So what are the goals? Of course, we want lower latency, higher reliability, and sustainability. But what that means, we need to capture, store, and process a ton of data. And we need to do that in an intelligent way and actually see where this best way is to do that data processing the right way. François Xavier, who I mentioned before, did his PhD on a not network related, but could be, a whole traffic management system based on just looking at the data of cars in New York City. He had no preconceptions. He looked at the data. Can we do the same in the internet? I think so. Another thing that we need to do is the protocols that are needed for sensors, for data orchestration. There was a draft early in this group about data discovery. Well, this is extremely important. Where is my data? Who owns it? Do I have access to it? And to orchestrate all these systems. And actually, of all these three, this is probably the one that is the worst, because there's more and more hurdles to access data. Some data is not open. Some data is protected by countries. And I'm lucky, I'm working with a group in Iowa State right now where we have our own wireless network. So we have access to everything. But this is not the case for everyone. And this is actually probably one of the biggest hurdles. And we can come back to that. And I think, Eve, the data discovery draft should address this thing right now, how data is hard to find. So data is the fuel of the 21st century. The goal would be an edge cloud information pipeline. We did a proposal with that in 4 years ago, 5 years ago. When this group was starting, it wasn't accepted, but that's fine. And I put the heterogeneous data system with a big H, because it is, like I said, a big problem. There's no standards in data. There's no standards in storage. I think data right now is where networking was before the invention of the IP packet. There's so many different formats, different granularity, different ways of recording the metadata, that it means all the time that the data must be clean. This ETL things that you hear about, it's not a joke. If you look at a lot of what is called data lakes, which have raw data, this is useless for decision making, for anything. It's just like a bunch of disconnected data things. And it's true for the edge, it's true for the fog, it's true for everywhere, including the data centers. And we need a lot of analysis. So why do I say partial correlation and lasso penalty models? Is a lot of times your data is not in the right shape to be used. You need to have independent sources. You need to have your data being completely decorrelated. If not, well, okay, you can do whatever you want, but then your decisions are going to be trivial. And we don't want to have trivial decisions. We want to have something that's going to help the network. I'm not, okay, this is another of these pictures where I could probably spend the rest of the day talking, but this is essentially what you do. You have your sources, you stream them with Kafka or something else, you get into some kind of unified database, call it a data warehouse if you want. You can feed digital twins, and I'm going to come to that. You have your AI engines, and then you try them. And the big thing is that this goes into your network supply chain. And that is not trivial. More and more, and I should have not called it a supply chain, I should have called it a supply network, because more and more, every element of your network supply chain has pieces of that. And I'll come back to that when I'm talking about independent intelligent nodes. So AI for the network and then network for AI. This has been, actually, it's interesting because this was a conversation I had with Henry Holtzman, who was at MIT and moved to San Francisco just before the start of the pandemic. And we were saying, okay, so at the time, and I don't know if Laurent Chavaglia is on the call, but him and I had done a lot of the beginning, and now there's a big thing in network management on the use of AI. And we had actually talked a lot about this. And what Henry told me was, because he came from the IoT world, was, sure, AI can help the network, but the network can also help AI. And how can the network help AI is actually through COIN. And this is another big link for us. And Dave, I'm going to answer your question later. Can I? And I'll come back to it. It's a good question. So sure, we can have a lot of AI, ML, who learns about traffic, learns about what's happening in the network nodes, but we can also have these smart nodes helping what happens to that data, to the functionality we need for AI to work. And a lot of time, because of delay, you do not have time to go to the cloud for each decision. You have to do a lot of things locally, or you have to do things, I would say, semi-locally, maybe in a RAN, maybe in another, I wouldn't call it edge, but further, a little bit further down, which is an aggregation point. And I think this is what I tell my students about this life of a packet. Think of everywhere where there is an aggregation point, and think about what you can do there to help to help the system, to help your AI, to help what's happening in terms of decision. So the issues are efficiency. Is this better than sending everything to the cloud? I think a lot of us think so. And I think it's in terms of efficiency of power consumption, it's also better. I could share with people some research that's been done here in Montreal on the difference of using the whole chain of network to the cloud, and not just what we have as data center in the north here, and how it saves on energy. Of course, we need physical models, which are very difficult, and data. Well, then you need a lot of data if you have to learn on your data. And again, I come back to what François-Xavier did at the Mila, which was he needed an awful lot of data to be learning from clusters and stuff. And the functional distribution, again, it's the life of a packet, but where's that life being lived in? So this is actually something very interesting for us, because it's at the center of the use of computing. And I'm going to go a bit faster. So this is the networked AI. I'm not going to, okay. So this is obviously a neural network. We want to have a lot of different elements in that neural network. And I would say the federated learning I'm reading Dave's questions. And obviously federating the learning is part of it. And no, Dave, it's not everything is all computing. It's needs to be related to the networking functionality. And yes, I think the all networking is the all encompassing. We're just going through down one path here. So digital twins, for those of you who don't know what it is, I'm going to go fast over this. A digital twin is just a software image of something physical, and it can be anything modeled. It started in the automotive and aerospace, but it's not. It's now been applied to all kinds of things, and I know people who are doing digital twins of plants, which is cute. For us, it's not that. For us, it's digital twins and networking. I realized at the Capgemini meeting that I was not the only one thinking about this, which was cool because it showed that it's interesting. There's a lot of work being done right now at Northeastern in Boston about twins of network systems and node. The great thing is that it's all across the stack. You can do twins of physical layer things, networking, network layer things, and application. It is much more powerful than traditional modeling because it's linked into the actual data from the network. You don't have to make that many assumptions. You can actually, in real time, check what's happening. The applications are management, of course, because it allows you to see what's happening in your network before you can implement your management processes. It's, of course, related to data and telemetry. Actually, from the beginning, there was this company, even in Montreal, was using Tofino to do telemetry. But network telemetry is extremely important, and that actually you can use your data, your digital twins there to see how the network is behaving, and then through the real-time exchange to actually verify that your twins is doing well. And one that is more important for me is testing. So you can actually do hardware testing because you don't have to send your real hardware. You could just email in a way or put your digital twin somewhere on a drive, and you could do your testing. And by the way, I will be hosting a networking channel on digital twinning and networking. I will go very fast. So the link to COIN, because we're COIN. We've talked about this, the network as a computer board, next generation of software, network softwareization, new hardware. You don't need Tofino. You can have a ton of programmable devices at every layer of your network, from the edge, the fog, and throughout to the data center. And you also want to have intelligence at every layer of the network. And it's interesting that the wireless people and ORAN, the Open RAN people, are actually doing work on that. And so it's all across the stack, and I think that's amazing. There's obviously common requirements, joint optimization, horizontalization, cross-functional, better integration. This is something that I could spend an awful lot of time, but this is something that I've been discussing with Dave Clark, was this idea of the decloudization and actually distributed decision-making. So created these intelligent network nodes, not having just dumb devices talking to one another, but just having them having the power to decide, am I capable of doing all these autonomous decisions, or do I need to connect to other things? So it's a view. It's actually almost, well, I think a generalization of containers, but it's also it's a network of neural network. It's all these nodes become nodes in your neural network. Obviously, it requires message passing. And again, we're coming back to functional distribution. I think information-centric networking has given us an incredible heritage for this. And actually, there's a lot of NSF platforms right now that are looking into this. And I think it includes important concept for 6G and IoT. And Dave and I call it the internet and the small, is that each one of these nodes is actually its small little internet. And thank you. Yes, decloudization is edification. Yes, I think it's you look at it from different side. So I'm getting to the end here. Some research, COIN and IETF opportunities. Obviously, AI, ML, AR. I didn't talk a lot about augmented reality, but it's there. And federated learning and network. It's interesting that there's going to be a full conference dedicated to this in November. So it is here, and it is just not for network management. It is across the whole edge cloud. Big thing for us to do research, we need to have open, private, and secure data sets, especially because of these heterogeneous environments and networks. We need real-time message passing, obviously the function definition, the composition and orchestration is extremely important. And I'm a fan of twinning because I come from the modeling world, and event-driven is so passé now. You need twins. Yeah, I'm a big fan. So as a conclusion, and I think I'm doing well in terms of time, because there's going to be time for, and I'm sorry to have rushed through this. You have access to it. I'm going to correct the typos and probably upload a new version. But so this is what I wanted from this presentation, to say that we were not Tofino. We were not Tofino. We were not just P4. We were looking at all kinds of programmable devices and how we were going to make this work. So essentially what COIN is promoting in terms of research, and I think you're going to see that from the presentations, because I read the other presentations in this meeting, is that we were looking as a research community for a programmable framework for advanced IoT and data-driven network automation. We want to have edge cloud and support for advanced network services, and we want to have applications based on and enabling AI and machine learning. And again, I'm coming back to this idea of the data with digital twinning and in augmented reality, providing the targeted services. So I know there's questions mainly from Dave, but I'm very much ready to answer questions. And I will try to answer the first question from Dave. Non-all trivial applications running inside cloud data centers are massively distributed. Yes, they are. But we're not talking of data centers here anymore, Dave. This is not, COIN is not about data centers. COIN is about everything from the time a packet leaves your device until it gets to the data center. I think it was maybe a mistake that we did at the beginning to really concentrate on data centers. And how about nano data centers, the things that happen in an IoT network, where you do have also there some kind of data center. So I get your point, but I think you probably missed the education and the decloudization. This is actually to get out of the centralization. And again, we don't have to be right. We just have to ask research questions. Maybe everything I presented is completely wrong, but frankly, I'd like to be proven wrong. And I think from my experience working in IoT systems, that I'm not that wrong. So that's
Marisha, I don't know if you can see, but we have also someone, we have Dean in the queue to
yes, and I think I went through Dave's questions. I think I'm against centrally managed, so you know that. So maybe we want to look at how to do decentralized management. And I think you guys in ICN have done a lot of work on this, and I think the distributed people do that well. So it's fine. Okay,
how about over to Dean then?
I think the big thing is that, I don't know what you think about not true anymore. I know about TPUs for AIs. In-cage.
Oh, you're looking at the chat window, and the chat window, I think, relatively speaking, Dave and I were just talking about the homogeneity of data centers versus edge continuum.
Yeah,
I think we're in relative agreement.
So I'm ready to take the other question.
Okay, great. Dean, go ahead.
We have 2 minutes.
Okay, Dejan Bogdanovic. So I'm coming back from the embedded world, and where a single system was handling everything within the same hardware. And as more and more distribution is happening, the embedded systems are sending the data all the way back to the cloud and then waiting and coming back. And in the industrial systems, there are 3 types of data. Some of them that if they're lost can cause a catastrophic event. Some of them, if they're lost, creates a problem, but still can be handled. And the third type of a data is like, if it's around, good, but it's not necessarily to arrive. Now, the problem there is not all the data has to be processed at a device, but not also at a central location, because there is some data that is important for some local neighbors that are working on the same function, but there are also some data that has to be processed with some neighbors that are working on some other functions. And there is a sort of hierarchical, well, I will say there is a topology of the data where it has to be processed, but today we don't have such mechanisms in order to do so. So there's a problem.
Who's your question? What's your question? Because I think I know what you're talking about.
No, I'm just saying it's a general comment. And then there's also problem about the connectivity between all those systems and knowing which connectivity is happening. So it's a multifaceted problem, but having distributed computing throughout the network is something that is stopping some industrial automation going forward. That's one part. And then is also the mobile connectivity in order to connect all of that together. So there are the 2 problems that are still out there to be worked on. And there is some interesting work here. And there's still some of research. I don't see real engineering problems coming out there yet. As more, there's a bunch of research to be done in the area.
Okay, so I know I'm out of time, but I'm completely follow you because I did that in an industrial setting. You missed also the fact that all sensors have different timestamps, different granularity, different formats. Yes, some of them need to be acted on locally. Some of them need to be acted on outside the system. A lot of sensing systems have very old-fashioned, outdated computing. The formats are wrong. The connectivity is wrong. Everything's wrong. But this is, again, this is the research. And I think you're completely right that there is a lot of research necessary. And since a lot of it is related to, oh, I like that picture. And since a lot of this is related to COIN, I think we have a good place to bring these ideas. So thank you. It's a very good comment. And again, it shows that you've been working in the trenches in this thing, because this is what is happening.
Colin, do you have a question?
You had a question?
Yeah, hi, Colin Perkins. This has to be the most badly arranged microphone queue I've ever seen in this room.
Yes, I thought you were going to tell me there was the room is a very odd room, but thank you for being here despite it.
Right in the middle of the queue. It's fantastic.
Yes, it's strange.
I'm sorry. I thought you were going to say it was the worst arranged presentation you've ever seen.
No, the presentation was very well arranged.
I was freaking out.
So thank you, Marie Jose. I think that was a really nice review of the area and a really nice vision for where the group is going. And I think it's important to have a vision, and it's important to understand the various use cases and what we may want to do with the work. I think it's also important that we have a bit of focus. It's important that we, as a research group here, build systems and build prototypes and try out some of these ideas. And check the designs and check to see if the vision is actually achievable.
No.
So, and I can see Jörg standing up to give a talk on part of that, and I think that there's another couple of talks which look like they're hitting that space later in the group. So I know the
it's actually I targeted my presentation after I saw what the other presentations were going to be. What are you suggesting could be the future of this?
So what I was suggesting was that I would encourage the chairs and the group to make sure that we don't just have
vision, that we also have implementation for testing and iteration.
And we don't just focus on drafts and standards and low-level things that are nearly finished, but try and hit the space in between.
Yeah, and you'll see actually in this session that we have quite a variety from vision to implementation.
And there's a really nice mix today, and I think that's good. And I just wanted to come up and encourage that mix happens, and we don't just focus on one
and I will tell you that what I presented is a subset of something that I proposed somewhere else, which was some kind of a 5-year research framework. So there's a lot of research in there. And no, I don't want to get into making sure that packets have the same format. I don't really care about this, but okay. I'm really interested in knowing that all these intelligent nodes are connected and can exchange information and create, more intelligent beings as they grow up.
Let's take the discussion elsewhere, but thank you for that feedback. Very helpful. We're just very tight on time with our presentations. Over to
and
you,
I did 4 minutes late. I'm not doing that badly. Okay, well, again, thank you so much, everyone, for giving me this opportunity. And again, I'm going back to being the chair now, so I'm not the researcher anymore. Thank you.
Okay, maybe then I'm up. Okay, let's add some running code. So we talked in COIN quite a bit about COIN is computing in the network, which means that some people think this is programmable switches, others think that this is little devices that are in data centers, racks or whatever, spread out devices at the edge, providing all kinds of services. And this is, Marie-Jose already alluded to the fact that The edge and the cloud continuum is important. And so this is some work that we have been doing, looking at devices that aren't necessarily switches, but rather little things, larger things, either in all kinds of different locations closer to, be it within ISPs, be it within mobile operators, be it within cloud data centers, or be it smart infrastructure and buildings or whatever. So I think there was already some discussion in the chat about the heterogeneity of the edge, and this is what this boils down to in the end as well. So the edge can be many different things. For example, constrained small footprint hardware. Raspberry Pi is, from a cloud data center perspective, clearly a small device. We might have even smaller embedded devices, that was also just mentioned. These devices may have special properties. We may have generic compute devices. Some of them may have certain sensors to fulfill certain functions. Others may have dedicated compute units. They may use all kinds of different networking infrastructure with all kinds of different properties, time-varying properties, sometimes more predictable, sometimes less predictable. They may be in public spaces, well connected to somewhere. They may be in private networks, not so well connected to somewhere, or harder to connect to somewhere because we have to go through nets, firewalls, and all these kind of things. And they operate in different environments and are operated by different people. We might have cloud providers who look after those. We might have, as I said before, ISP, mobile operators, or all kinds of private entities running their own compute devices or managing their own compute devices. And this gives us a decent set of heterogeneity along a couple of dimensions that all want to be treated when we think about how to pull these things together to create a computing environment in some kind of distributed fashion. Now, of course, when I want to run things on these, all kinds of these different devices, I also need to have a way to abstract from them. So I would use some kind of virtualization techniques, be it containers, be it, because we have also small devices, more lightweight runtimes like unikernels, or then maybe even process virtual machines and the likes, all the way down to eBPF or something maybe. Where does the next, hello, next slide.
You want me to move it?
What did I do with this thing?
I think what you did was you had, hang on, let's see. You're just adding bullets. So there's the next. There you go.
There we go, okay. We mentioned already AR. So this is typically edge applications might be trying to do either something very fast, so you don't want to have the computation close to where your user device is, but in general, you perform computations that aren't being done on the device themselves, either because the device isn't capable, doesn't have the necessary data, or is just the other infrastructure can just do it faster. So a simple example would be this little AI processing pipeline here, where we have maybe a packet sequence stream coming from a camera that gets into an aggregator that takes all these packets, reconstructs complete frames from those, then feeds them into an object detection mechanism after some pre-processing. And is the little red bubble in the middle that identifies different objects and sends those information on to a tracking service. So you might put all of these things into a single application. You might also, as we nowadays often do, decompose this into multiple microservices like this is indicated here. And then we need to stitch these microservices together by having something like a processing pipeline, or more general, a distributed directed acyclic graph, a DAG.
You have to point over here.
Oh, I have to click over there.
Is it moving?
Oh.
Maybe the battery died. Yeah. Do you need me to click? There you go. I'll just tell me to.
I'll just tell you next. Then I'll take this thing out of my hands, that I at least don't work with that. So these different microservices decomposing applications doesn't make sense because we may have different scaling properties. Some of these may have very simple functions that can serve many clients, maybe like the simple aggregation and packet processing thing that just does some decoding on the left-hand side, whereas object detection might have more power requirements, and therefore you'd like to replicate this in order to have either different objects detected or run different instances in parallel. And similarly for tracking, you might then have different relationships between the individual components. Next. In order to make these then reality, besides just stitching them together, you need to also instantiate them somewhere, right? We need to have physical nodes that can execute these individual functions, these individual microservices, and they need to be allocated. You need to have some kind of logic that allocates these functions to these different nodes, potentially taking into account the respective capabilities, the current load, and so on of these different nodes. We all know how this is done in the cloud. We have services like Kubernetes that takes care of these, has a control of many different nodes, understanding how they are currently performing, and then allocates new task assignments to these different nodes in order to run there. Next. This is where the specifics of our edge environment come into place, right? We talked about earlier about this heterogeneity. So we have more diverse devices. Usually data center infrastructures are fairly homogeneous. You may have different types of devices, but then you may still have thousands of them. So scaling and so on is relatively easy. Similarly, all data center nodes are usually close together. A microsecond ping RTT or even below might be something that you would commonly experience, whereas in the edge, not necessarily you may have things that are connected wirelessly, things may not be in the same physical location, connectivity may not be as guaranteed as in a data center and so on. So we get also network diversity. And then of course we may have different operators who run these things. So we have a greenish, a brownish, and a grayish operator that is running that are taking care of different devices. And things like systems like Kubernetes are targeted to operating within a single administrative domain because you want to be able to tightly control each of these individual nodes. And tie those tightly together, always knowing exactly what is going on which of these nodes, which of course also creates sorts of communication overhead. Now that doesn't work as easily as the edge, but in order to cope with some of these issues, a bunch of systems have been derived from Kubernetes, like K3s, micro Kubernetes, and so on, in order to take care of these specifics, but that they don't quite get there yet. And this is next. This is why we took a different approach and thought, well, maybe rather than trying to work straight from this starting point of a completely synchronized, homogeneous platform and then try to tier out some of these things in order to make them more distributed, we took the opposite approach and started with a distributed design assumption and built something called Orchestra in order to allow accounting for these specifics and diverse elements of edge computing. Next. So Orchestra does many different things. I just can talk about a few of those here, and there's especially the ones that are relevant when it comes to managing distributed edge environments. So the title of this talk already said it's hierarchical. So we have a hierarchy here. We have a root orchestrator, and we have to have a bunch of clusters. So we are grouping resources into typically physically co-located clusters of things that are then managed together within some local administrative domain. So we have this greenish or yellowish, the brownish, and the grayish administrative domain. Each of those managed by being one cluster, managed by one entity responsible for this cluster. Let's start with these little blue nodes down there. Next. Obviously, the first thing that we'll need is workers, right? We need to have workers that have an execution runtime where you can deploy a container, or nowadays also a microkernel or something else. So, for example, containerd, using that as a starting point. So this is where our whatever services you'd like to execute get run. Next. Then we have a node engine. Somebody needs to oversee this execution itself with two specific features in there. One is, of course, you need to understand what capabilities your node has so that you can actually tell to an orchestration system what the node is fundamentally capable of. This includes, I don't know, total memory, number of cores, number of GPUs, what have you. At the same time, you also need to be able to understand what the node is currently actually, how loaded the node is currently is. So which are the services that are currently running, how many resources are they using, and so on. Next. So that's the node engine that takes care of this. Then we also have a network manager, because a node, as we saw before, next, might interact or would interact often with other entities or any single entity any single function that we might want to instantiate would interact with another function, be it on the same node, a different node, in the same cluster, on a different cluster. And somebody needs to manage this connectivity. This is what we have the net manager for. That understands which nodes need to talk to whom, gives each applications their individual namespace, and then ensures that the different nodes can talk to each other if necessary, creating tunnels across the different clusters, so where we have then net traversal functions, all these things built in. Next. So that's our worker node. Of course, our cluster will have multiple worker node. Next. And next. These worker nodes then talk to a so-called cluster orchestrator, which is the thing that has the local oversight. We use an MQTT for communication. We have a simple pub/sub-based system. Each of these workers, next, reports their individual current usage statistics to the cluster orchestrator. The cluster orchestrator itself has a name, a location, and so on, and then has a bunch of different databases for services, for the nodes that are existing and the networks, and then all the different statistics that are gathered for the services, for the nodes, and for the net. This is all very nitty-gritty detail about what is going on at any given point in time in any of these nodes. And it has a cluster manager that understands how the overall cluster is loaded, that aggregates these kind of information. It's a service manager that understands which of these nodes are currently executing which services, and was able to create new services and then utilize the cluster scheduler to put them into practice or into execution on the different nodes. Next. Now we move up one level in our hierarchy, we see all the different clusters. Next. And these different clusters, as we said before, might be operated by different entities. And of course, if I'm running something, I don't want anybody else to look in detail, understand in detail what am I doing inside my own cluster deployment, how am I managing my nodes and so on. This is actually nobody else's business. It's a bit like, well, if I'm running my own little network, I might expose general routes that I can support to other entities, to other ISPs and so on, but I wouldn't share necessarily the intrinsic details of how my internal routing works. And so we do something similar with compute resources here. Next.
Sorry, I'm also typing into the chat window, so my apologies for the delay.
No worries. So these cluster nodes do provide aggregate reports. So they rather than saying I have 15 different machines and they have all these properties, no, we just say, oh, in total I can do that many CPUs, I have that much memory, my current load situation is 60% and so on. So we have an aggregate reporting that goes up to the root orchestrator. The root orchestrator, as you can see from this figure, has roughly the same components replicated that we also have at the cluster level, except that it manages the entire deployment of such an orchestration system, but it only sees coarse granular information. Enough to understand, oh, this cluster over there is loaded, well, this cluster here is empty. So if I get the next job, I'd rather push this to the empty cluster. Or it might know that, oh, this cluster is sitting in San Francisco, or it's sitting in the Hilton. And therefore, if I want to have a fast executing service or fast responding service for somebody who's in the Hilton, I should probably deploy this service on that specific cluster because of its location and topology. So other than this, we have roughly the same components. Next. If I now want to specify a service, I create some kind of, in the end, JSON represented documentation that has, for example, says I have one aggregation unit, I have two different object trackers that look out for different objects. They feed the respective output of which objects they found into a tracking system, and that then works and tracks these objects. And for each of my services, I can specify a namespace, how the entire application is called, and then my respective needs in terms of memory capacity, CPUs, if I need GPUs, or any other special requirements I might have. Next. This specification I can push into my root orchestration system on the top left. Next. And which effectively means that this goes into the service, into the system manager. Next. Which will then ensure that the respective code that I'm going to need for deployment will be stored somewhere locally in my respective services database. Next. If I then want to deploy these, I'm going to issue a deployment request that specifies, for example, certain constraints to our root orchestrator. Next. which means that first of all, there is a deployment request. I'm going to fetch the respective code that I have readily available, and then ensure that I'm going to get this scheduled. At the root scheduler, I don't take very fine-grained decision, as I said before, but rather figure out which clusters would be available at this point in time to fulfill the requirements for this respective service. Next. And in this case, it's decided that cluster 2 is going to get 2 of the components, cluster n is going to get 2 other components, which also would mean that in the end, these respective clusters would need to see some kind of interconnection happening by the aforementioned network managers to establish communication between those. Next. While the root orchestrator just picks the cluster, it delegates the responsibility for figuring out how to make this respective scheduling happen inside the cluster to the cluster scheduler itself. And so the cluster scheduler then receives this request, receives the respective code instances, and can then make a deployment decision on where to put these. Next.
Oh, and if you could finish up in a couple minutes, that would be
yes,
awesome.
I am about to do so. Okay. So these things get deployed on the respective nodes. Next. And the cluster scheduler then decides which specific nodes they should be running. The plumbing sets up the network plumbing sets up the respective interconnectivity between those, and we are done. Should for whatever reason a cluster figure out, because it's reporting only coarse-grained information to the root orchestrator, that a particular service can't be instantiated, then it can actually delegate this responsibility upwards again and tell the root orchestrator, oh, can't do this right now, please find a different location, which means that at this very moment, we don't have to have every second detail insight on what a cluster does, but we can utilize these kind of similar rough abstractions here. Next. Since I'm about to finish up, so we built the whole thing. This is currently a relatively lightweight implementation. It's, at the moment, so it's open source. You can find this from orchestra.io. You can find it on GitHub. It's currently 19,000 lines of code. When I talked about this 2 weeks ago, it was 18,000 lines of code. So we have a nice growth. I can't promise that this growth is going to continue every 2 weeks. It's mainly Python for all the orchestration components and Golang for the network, the efficient networking components. It is modular so that different scheduling policies can be added. The design itself is modular to begin with. And it is sufficiently lightweight and also reduces the amount of effort that you need to put on the edge devices because, hey, after all, they're supposed to run the services. Next. Performance, the last bullets, it compares favorably with a bunch of other systems. This is just a sample plot here to show that for a simple cluster deployment with one root orchestrator, one cluster orchestrator, and a bunch of workers, the abstraction level between the root orchestrator and the cluster orchestrator works because on the right-hand side, you can see that as the number of workers increases, other systems that have minute detail of all the individual workers do grow in compute requirements, whereas Orchestra doesn't, simply because you don't get all these detailed reports all the time. And also workers are very lightweight and support in terms of the CPU overhead, which also allows us to run stuff on or deploy code on devices that the other systems can't even do in the first place. Next. And that's it. So this was a bit high-level overview of the part above the surface. If you want to look below the surface, go to orchestra.io, read the code, read the paper, ask us. Thanks. Questions?
Looks like I'm in the queue, so I'll take off my chair hat.
Yes.
One of the discussions, or at least comments that appeared in the chat window as you were talking about cluster formation and then clusters of clusters was your reference to MQTT. So, you know, this reference to both an inter-cluster comms and an intra-cluster comms, and are they the same and different, and how are they, and what did you use? What are your thoughts about that?
The inter-cluster, well, the cluster orchestrator to root orchestrator is actually RESTful API using HTTPS. The intra-cluster stuff is MQTT because there we want to have fast reaction times with notifications and everything. The rest towards the root orchestrator is very low rate, low frequency. So if we would be updating within the cluster maybe every second or faster, we might be doing this every 10 seconds or every minute at the next higher level, if that helps answering the question.
Sure. Diego, did you want to ask your question? I know this is a very odd queue. For those of you not in the room, you can see the column there.
People show up behind the trees, jump out.
I was just, no, Colin had some issue with his iPhone, so I overtook him. No, just a couple of questions. You showed this idea of the different, I mean, the clusters belonging to different domains, etc. Just out of curiosity, I mean, in terms of administrative, the orchestrator, the main orchestra thing, where is expected to live? Because
there is not a single one, right? You can't build a single system where you would expect a single one. So if you would want to do something in this corner of the city, you might want to run an orchestrator that provides services for a given set of applications for a given part of a city, of a region, or whatever. And so there is not a single one. This also means, but because you want to utilize resources from different people, they might be exportable, or that you might have different clusters that export their resources. Now, there is no one-to-one relationship necessarily, which means that if I have a bunch of street lamps that can do services for people, I might sign up with multiple things because there could be sensing for multiple purposes, and I might be able also, or if I have some other compute resources, my cluster might be part of multiple root orchestration domains, because I'm not reporting every little nitty-gritty detail. I could do oversubscription. I could share 50% with one entity, 30% with the next one, 40% with the fourth one. So because there is no way that you could ever possibly agree on where a single thing would live, it's designed to be allowing operating with multiple roots, if you so will.
You know, with all the hassle right now about the multi-cloud, federated cloud, etc., I mean, or moving to multi-edge, federated edge, something that would be interesting to
in the interest of keeping on schedule, I'm going to unfortunately close the queue. Okay.
And I was looking at those.
No, there's quite a long queue, but I will suggest that people take things to the chat window. Maybe we can continue there for now.
Second, very short question about the networking patterns. You're using some kind of overlay, or I mean,
they're constructing a simple overlay, yes. But and that is fairly lightweight as we measure it, so the performance impact is fairly minimal. But there is a bit of overlay yet. You need to do this. So we use a lightweight tunneling protocol between the different nodes. The Azure resolution happens via the root orchestrator, but only for initial resolution. Then the rest is being cached the moment you have been setting up something. And because this is also often being asked, if one orchestrator fails, the services continue to run. Be it the cluster orchestrator or the root orchestrator, they would only be affected. So you could actually fire up a new one that could then gather the current state of the information again and continue. And this is why it also wouldn't affect the ongoing tunnels, because they're all running directly peer-to-peer.
Let's take this to the list. It's just we have such a crammed schedule. Or to the chat right now, okay?
Okay, thanks.
And we can continue on chat. Okay, so Sharon, are you online?
Yes, I am. Can you hear me?
Yes. Would you like to drive, or shall I?
If you can, that would be great. Okay. Thank you. Okay, I apologize for my voice. Yes, I do.
Excellent. Thank you.
My voice is a bit sore. I managed to get a cold in the middle of the heat wave. I don't know why. Air conditions. So if I'm not clear, please indicate. So this talk is about share nothing edge AI using pipelines explained through mobility network functions. And as Marie alluded to before, it explores a recurring theme in COIN of using logical addressing and overlays to implement computation networks. But this time we're emphasizing generative AI and using mobility network function as an example to clarify it. So next, please. All right, so at the philosophical level, We all know that there are synergies between cloud computing and the network cloud, but in pure form, cloud computing thinks of the network as a bus, sort of like an InfiniBand bus, and access links linking the world to this big computer, big warehouse-sized computer. And in pure form, the network focuses compute in junctions with very rigid and standard logic, which is interoperable and interchangeable. But the synergies between them produce non-pure, but very interesting and very effective share-nothing pipelines that have been helpful before. For example, CDN, you can think of CDN as a share-nothing pipeline where you ask for a URL content, you're steered to a cache. If there's a cache hit, then you serve the content. If there is a cache miss, then the origin is asked to get the content on gigabit links while the content is delivered over megabit links. And nobody assumes that the caches share any storage, or the caches and the origin share storage. And this allows CDNs to scale immensely well. And we are going to add another such example with share-nothing pipeline with generative edge AI. Next, please. All right, so basically, we're looking at share-nothing, at the share-nothing cloud, share-nothing pipeline as a network. They do not use the cloud as a big computer, meaning they do not allocate processes anywhere, just anywhere, using some kind of EC2-like operating systems, and they do not assume an S3-like shared data plane. Instead, the data flow is contextually routed rather than randomly load balanced. And because we do not assume any kind of shared storage or any speed-up bus, like a spine leaf in a data center, we are able to geo-distribute the computation, and the east-west capacity needed to support the service is in direct proportion to the north-south service itself. So if the service itself is at 10, 20, 30, 40 gigabit per second, the east-west is not much more than that. Unlike looking at the centralized cloud as a big computer, where we need 100 times, even more, multiple 100 times capacity east-west for any north-south service. Next, please.
Oops, sorry.
Yeah, so a well-known example is NFV service function chaining. These are clustered programmable functions. Still, they operate in wire speed, serving entire network providers' traffic, because really the functionality was conceived as an appliance or as a module within a router, and the whole pipeline was part of the traffic engineering. So because these functions were conceived this way, we're able, as SFC is able to sort of abstract the traffic engineering flow and distribute the computation and in full wire speed for the entire network, even though it was clustered and it's no longer an inline appliance. Next, please. So we use similar approach in implementing and specifying mobility network functions in the automotive edge compute consortium, specifically geolocation, which is a typical edge use case because it consolidates immediately information from multiple vehicles for multiple vehicles. Therefore, it cannot be in the cloud because of capacity and cannot be in the car. And the way this share-nothing pipeline works is that, for example, a vehicle spots a free parking spot. The detection is uploaded to an area agent responsible for that area, which consolidates that information because it may be gotten from multiple vehicles, from multiple points of view, localizes and generates notifications for the vehicles looking for parking. So next, please. Okay, so this is based on the Lisp RFC set, where we use Lisp in order to assign logical IP addresses to agents and based on their geospatial jurisdiction. And we use EIDs, and we use also EIDs assigned to the vehicles so that their geoprivacy is protected while they are producing and consuming data. So Lisp here allows us to build an ad hoc cloud, meaning we don't know why and when a specific agent will reside in which edge location. This is a DevOps decision based on the density, like it's a commute or it's in the middle of the night. If it's commute, I'll spread the agents more, less agents per compute location. And if it's the night, I'll condense. And we don't know when a vehicle is going to join this cloud or leave this cloud, but the Lisp acts here as a sort of like layer 3 Kafka. Fully distributed and terabit per second, and helps us scale notifications. The extensions to Lisp allows us to assign logical addresses to geolocation, and also sort of streamline a language of data. I know Marie talked about it, sort of streamline the data that if the jurisdictions are tiles, then so are the metadata. They're all mini tiles. If the jurisdiction is square kilometer, a detection is a square meter. I mean, what I have to say about a square meter in terms of geolocation. And next, please. Okay, so this was all very nice. And then what happened in the last year is generative AI happened. And the importance of all these architectures became a lot more interesting. So generative AI, as most of you probably know at a high level, and I mean, I'm not expert in the details, but it's basically able to process input language through attentions and generate output language. And it really, what it did to our roadmap is it accelerated like many orders of time. What you can do with generative AI is a lot more powerful than what you can do, for example, with Vision AI. For example, with Vision AI, if I want to train on detecting an object like a cone, a traffic cone, or a parking spot, I have to do it for every lighting, for every resolution, for every angle in every country. It takes forever. But in generative AI, I'm able to segment images using models that were trained on a huge amount of data. And I'm able to label these segments and localize these segments using generic foundation models that were tuned for this task. So the impact on features is dramatic. I'm astounded every day anew. So we want the network, the pipelines to leverage these generative models, because no one model does the entire job. You need a sequence of things, and you need to sort of translate from one to another until you get the results that you want. One does segmentation, another one does labeling. This are completely different tasks. So we want the pipelines to leverage that amazing technology, but we also want it to mitigate some of its two most difficult key issues. Key issue one is that it's very slow. From the time you go into the prompt and the time you go out as a response or a query response, it can take hundreds of milliseconds. So it's nowhere near like Vision AI, or definitely not like code. The second thing is that this requires a huge amount of compute capacity. So we want to be able to leverage the network to solve both these problems and engage generative AI in the mobility network. As an example, next slide, please. Okay, let's take a look at as an example, which is was futuristic 8 months ago and is now a live POC, a semantic virtual cam. This is sort of cameras hovering over the city, each one looking at a square kilometer, and they don't really exist. These are virtual cameras. The camera is actually fed by images from driving vehicles, But rather than have just a collection of images, just a salad of images from different angles and different resolutions and different places, the virtual camera employs a segmentation, labeling, localization pipeline, ending up with a language describing what's going on in that area, which is noteworthy, which is worth attention. An event, a change, a situation, a congestion, a blockage, a results of a blockage, and things like that. So this would be possible with the Vision AI, but it will take, it will take forever, and it's very, very difficult. With generative AI, we receive that result immediately from off-the-shelf foundation models tuned for those tasks, and it's really extraordinary. We also see that generative AI here plays to the strength of OEM because it's based on a lot of data. And the one thing OEMs have is a lot of data because they have millions of moving sensors all over the place. On the other hand, it mitigates weakness of OEMs, which is agile, dynamic code. Yes?
Sharon, you have less than 4 minutes.
Okay. So I'll run. We also see that the fleet here solves the time problem, okay? Because the future of the cars on the right is the present of the car on the left. So I have enough time to deploy the generative AI pipeline. So next, please. Okay, here we see that we can combine multiple input sources like satellite, drones, something that would be impossible with Vision AI to do in a reasonable time. Very simple with generative AI. Next, please. Okay, and this is the POC plan for later this year, extending the last year's POC of parking. Next, please. All right, now the second problem is compute resources. And here we see also that the fleet or the connected fleet and the network can help solve that, because obviously the driving vehicles are very busy with perception and for planning ahead based on generative prompts, but the parked vehicles are completely idle. And we're talking about petaflops of GPUs going into electric vehicles because of software-defined vehicles and centralizations of computing vehicles that they have to be there anyway. And because of the pipeline, we're able to leverage compute resources wherever they are, even if they're on the far edge at the vehicle. While it's charging, it could be Ubers or leases or anyone who agreed to a discount because it helps the fleet. And because of the anyway high latency of the compute, it's okay to use the far edge. Next, please. Okay, next. This is like military use. Next, please. I won't get into that. So in summary, we see the Share Nothing pipeline is really a network, and it can really help us leverage the power of generative AI, but also mitigate some of its weaknesses. Next and last slide, please. As an example, if I were to take a 1 million active cars city like London or New York in peak time, over 1,000 square kilometers, with a 10% sampling rate of 100,000 frames per second, that would be 100,000 frames per second will create 100 gigabit per second pressure on the uplinks to a remote centralized cloud, which will require 10 to 100 terabits per second fabric in order to randomly compute all that, and will require an extraordinary amount of GPUs concentrated in one location. On the other hand, if I break it down to these Share Nothing ad hoc clouds, I end up with reasonable size problems in much more self-sustained jurisdictions, sort of living off the land of the GPUs around them, like a 1 gigabit per second, and I need like 10 agents, and I can allocate this dynamically between compute locations which are currently available. That's it. Made it.
Well, thank you very much for the interesting presentation. Do we have some questions? It's super interesting about, I really like the theme across all of these talks so far, of the clusters of clusters. And I really appreciate the doing the back of the envelope calculation on what the fabric would need to look like, which of course doesn't exist as yet, right? So you did talk about, you had multiple POCs. So what is do you have some toolkit that you're using and reusing for all of these?
Yeah, these are public ACC POCs. Last year was just to find parking, and this year is just gonna describe the location in a language, which can then be prompted into models that generate like Unity, GPT, visualization, things like that. So from a bunch of pixels to streamlined language of the tiles, and from tiles to applications like navigation. The ACC specifications are not a toolkit. The Lisp stack is open source. I mean, there's multiple sources for that. Maybe Dino or Alberto can point you out to that. Using the addressing scheme that's based on the RFC extensions to Lisp. And besides that, just take these foundation models. There's a new and better one coming up every other day. It's just extraordinary. And don't code, pipeline.
Yeah, exactly. Okay. Anybody else? Terrific. There's also some relevant chatter going on in the chat that I'd suggest you look at as well, about addressing and identifiers that seem relevant here as well. Thank you so much.
Thank you very much.
Okay. I think we are ready for Jung-Ah. Would you like me to share? Let's see. Would you like the terminology or the use case analysis?
Oh, the use case analysis.
Okay.
Hello, everyone. This is Jung-Ah Hong from IETF in Korea, and I'm very happy to taking over this draft from Ike, who have done great work about this. And next slide, please. And since I have taken over this draft, I had to take a deep look over the draft. And during that, I realized that this is really important and you will be useful document for the COINRG in the future, because it was separated from the use case draft. The use case draft describes each use cases with the use case driven requirements or opportunities and research questions about it. But on this analysis, it is providing the identify the commonality of all the use cases. So I think this is very useful work for COINRG. So during the reviewing the draft, I made editorial changes and also added some description about on the categorization on the research questions. There was a couple of things was missing in there. Next slide, please. This is the purpose of the draft, which is to analyze the opportunities and research questions and requirements of each use cases provided by the draft of the use case to identify the commonalities. So by doing this, we really like to provide the general direction, research direction for the COIN. So this is very useful work. The current title is the use case analysis, which was a part of under the use case draft. I think at the time it was okay with the title, but since it has been separated from the use case draft, I think we are proposing to a more proper title, like research challenges of computing network, or the opportunities and challenges of computing the network, or something else. If you have a better idea, please comment or suggested. Next slide, please. And this is the current status of the document. The analysis part was composed of the research questions and opportunity and requirement, but still the opportunity and requirements are missing. But the content of the research question was provided through a layered categorization like this picture. Next slide, please. So this is the future plan that, as I already mentioned, we like to change the title to the research challenges or opportunities or challenges like that. So by doing that, we like to make the scope of this draft, make the broader and more make generalized. So we try to focus more on the opportunity and challenges, so the requirement might be deleted later on. But to achieve this, we really need more contributor, because this is very important. This will be a very important document or base document for this group in the future. But we need to collect all the common understanding of the group about the research direction for the coin. So we really need a contributor. So please send me an email or talk to me if you are willing to become a contributor. So yeah, that's it.
Great. Okay, let's go to the other draft, which if you have, oh, no, I don't want to share the screen. I want to share slides.
Okay, this is the terminology for the coin. Again, I haven't taken over from the AG, who have done a lot of work for this. This is also was a part of the use case draft. And there was a number of use cases which use the different terminologies. So when they derive the merged all the use cases in one draft, they needed to define the terminology. So from that, it was started, and then later on, it was separated from the use case draft. Next slide, please. So again, I only made several editorial changes for now, and also we added one more terminology for in this revision, which is the coin function. It's a specific computational task that can be invoked as part of the program, and it contributes to the overall functionality of the program by providing a modular and reusable universal computation. Next slide, please. And the purpose of this draft is to bring clarity to the current understanding of the coin. So all the terminology was collected from the use case draft, as well as the direction for the coin draft, which has not been updated for long. So I have talked to the Dirk Kucha, who he has some plan for updating, but I'm not sure, even though he updates this draft, then we'll have a new more terminology for this draft or not. Next slide, please. So for future plan, I would like to ask the questions to the group. Actually, this question was issued by the Maria in the previous COINRG meeting. That the question is, shall we just maintain this document as maintain the current version, and whenever the new terminology comes up, we can add or we can change it whenever it is needed, and keep going and until at some point, and then when we think it is ready to publish, then it can be done. Or if there's no more comment on this terminology document, or if the group thinks that it is ready to publish it, or then we can move to this terminology draft to the RG law school, because the authors, I really think that in the current situation, there isn't, this is all that we can collect, the terminology that, although there are very few terminology in this draft, but just we can't do anything more.
It's a very short draft for those of you who haven't looked at it. But it's very helpful.
Yeah, sure.
So we need probably more commentary. It looks like we do have a question from Dean. Mm-hmm. Would you like to step to the mic?
Excuse me. So on the draft and the terminology, it's good to have one set and saying like this what we are using, so that we don't have overloaded terms when we are speaking. But there is, as with the terminology, it's always a living thing.
Completely agree.
So that's one thing. And then the working group, the research group has to be ready to produce. I don't know if there is a BIS in the
right
in order to update the terminology. Hopefully not changing the existing one, just adding new terms to it that are starting, to come up. Also, I would prefer to keep the use case draft going forward, because use cases.
Use case or use case analysis?
Well,
there are two.
Use case.
Okay.
So not rename it. So like keep the use case draft, and not to look into research and the opportunities, make it as a separate research, like a separate draft, and keep those two separates, because use case can be very useful for what is a current problem, and then research
so the
and
use case, so there are two drafts actually.
Okay.
There's a use cases draft, and then the use case analysis. So the proposal here is to change the title of the use case analysis draft,
okay,
which is a cross-cutting one.
Okay.
So I think we're actually in agreement.
Okay.
Okay.
Yep.
Thank you for your comments, and I'm hoping, Colin, you will have a brief comment or clarification about maybe the IRTF process here for terminology and use cases.
I mean, in terms of process, if the research group decides it wishes to publish them and has consensus, then it can request they be considered for publication. What I came up for, I mean, having common terminology, I think, is a good thing. It tends to make a lot of sense if you are building, if a group is building a system, like we see in a lot of IETF groups, where we're agreeing that the terminology we use to help design a system to avoid talking across purposes. And I think it can help in the research world if there is evidence that the broader community is adopting that terminology to try and help organize the work in the broader research community. Without really evidence that either of those are happening, it's not clear that there's much benefit.
Well, I think. Would you like to comment?
And I don't know if either of those.
Because I have an opinion as well. Yeah. I'll put myself back in the queue.
But I guess one of the things we would be asking before publishing a terminology document is it getting traction, or is it likely to get traction?
It's like to get the common like understanding of the terminology in this group. That's the purpose.
Right, so that when we use the terminology in the group itself, that we're all talking about the same things. And I would agree with Dean that although it doesn't need to be published per se, having an up-to-date terminology draft as the area continues to evolve would be very helpful.
I think it would be helpful if it starts to get traction and people start using the terminology.
Right, and so the question, so it remains to be seen whether, if we're producing other documents and other presentations, whether we can codify and accelerate the adoption of these terms, and if people find it useful and intuitive.
Yeah, indeed, and whether the broader research community starts adopting similar terms.
Yeah, thank you. Okay. Thank you very much.
Thank you.
Where are we? We are now into the final stretch where we have a couple of individual drafts. So let me propose that, let's see, who's next? We have Luis Contreras, the evolution of class, cooperating layered architecture for SDN for compute and data awareness. And unfortunately, the clicker doesn't work, so I will share your slides. Whoops.
Thank you.
But it would help if I clicked on the right button here. All yours.
Thank you. So this is Luis Contreras from Telefónica. I will present an update of the draft, which essentially presents an evolution of the cooperating layer architecture for SDN.
And may I request that you try to do this in 5 minutes? I think that was what was on the original schedule. I just wanted to say it out loud.
I'll do.
Thanks.
Okay, next, please.
Okay.
So as a background, the cooperating layer architecture for software-defined networking was released as an RFC. And it essentially an origin proposed a separation between service concern and transport concern. So create, let's say, separating the control, management, and resource plane devoted to each of those strata. So this separation allows independent evolution of service control and transport control, and so, and also, I mean, and despite being separated, requires the need of having a tight coordination in such a way that the overall optimization of the service and deployment of the service is consistent with the expectations from the user. So what we did propose in this new draft is an augmentation of this architecture, of the class architecture, essentially adding a new strata, a new stratum devoted to compute, and also creating a new plane or proposing a new plane which will be devoted to data awareness. So next, please. So this is the original class architecture. As you can see, there is this separation of concerns. In each of the concerns, we have management and control plane for in one case devoted to the service itself, so it will be to the function, service, or application, and in the other case for the transport, for the connectivity. And also we have the resource plane, essentially trying to handling the resources applicable to each of the strata, resources for the service and resources for the connectivity. So next, please. So the first augmentation that we are proposing in this draft is to add a new complete stratum devoted to compute, again with the management, control, management plane, control plane, and resource plane. So somehow in line with what we have seen in the session today. Note that despite the representation seems to be hierarchical, this is not hierarchical. This was one of the comments received in Yokohama, so we will try to figure out how to represent this in a more affordable way. But just, I mean, we are structuring this way just for visual look and feel. So next, please. So the second addition was this telemetry plane. In the previous version, we call it learning plane. We have now changed the name to telemetry plane. The idea would be to have this plane devoted to the collection of data that later on can fit control loop capabilities, artificial intelligence, and all this stuff. So next, please. That would be probably a better representation of that, so avoiding the hierarchical structure. So probably we will need to do something like this in the new version of the draft, trying to put at the same level, let's say, the connectivity and the computer stratum. But anyway, as a summary, you can see here the augmentation of the new concern, the computer stratum, and also the inclusion of the new telemetry plane in order to complement all the control capabilities. Next, please. So the changes essentially was the renaming from the learning plane to telemetry plane. We think that this is much more clear, let's say, the purpose of this plane. So the idea would be a set to collect for each of the strata the relevant data and then allowing the processing of this relevant data in each of the strata, even though the idea would be to maintain collaborative interfaces between the different strata in such a way that for all the planes, in summary, there could be this cooperation at the time of deploying the services. Second, we have improved the description about the potential research aspects of the telemetry plane, of the learning plane, so there is more text in the draft. And finally, we have included some applicability scenarios. First, the cloud edge continuum, so considering an environment where we will have separated compute capabilities attached to the network, even the network being both network and compute being from different administrative domains. And here, highlighting aspects that probably could be ways of I mean, ideas for researching, like optimizing resources in both compute and network, guaranteeing services SLOs at the time of doing the services, or even secure transmission of the information between the different planes, the different strata, the compute and the connectivity strata as well. And then the second applicability scenario will be the network application integration, where the idea is, as today we have decoupled a situation where the services are decoupled from the reality of the network, and the network in a broad sense, I mean connectivity plus compute. So the idea here would be to exploit capabilities of exposing information from the network, also collecting telemetry in order to apply artificial intelligence capabilities, and maybe other aspects like maybe using metadata across the compute and connectivity strata, that metadata being defined by the service stratum. Next, please. And the last one is essentially next steps. We acknowledge that we need yet probably to set a little bit more on the scope to COINRG the purpose of the draft. So we will work in that line with all the use cases reported and terminology and so on so far. We would like to collect feedback and interest from the research group if any of this is essentially interesting for the research group to continue working on that. And prepare new version for next IETF, and with probably fixing these diagrams and so make it more visual, let's say, that idea that not having a hierarchical relationship between the compute and connectivity. So that's all from my side. Thank you.
Great. Thank you very much. And thank you for being so clear on what your expected next steps are. Marie-José, you have a question? We are not hearing you.
No, I think you now do. I think this is interesting work, but at the same time, I am questioning why. Yeah, this layered architectures are very standard. So I would be interested in seeing what do you think your approach is different from other layered architecture that do have computing and aggregation and everything. And I think that would be nice to highlight that in your draft, because I read it. So maybe you can comment on that.
Yeah, so basically what we see here is the interplay between the three dimensions, the connectivity, the compute, and the services. We think that we need to keep all the three combined in order to do things like resource optimization and this kind of aspects. So probably that would be the novelty part, I guess. So trying to work on this interplay of the three dimensions simultaneously. And I mean, the three strata, but also the planes within the three strata, because the idea would be also for instance, in the case of the telemetry plane, interplay as well the telemetry planes on the three different strata. So somehow it's a kind of dual interdependency at the strata level, but also at plane level.
Okay, Dean?
Dan Bogdanovic. So I have an issue with the telemetry plane naming, because telemetry can be part of the data plane and can be part of a control plane. Yeah. And depending what type of characteristics you want to get, you will choose one or the other. So telemetry is always part of those two planes. How do you see that as a separation?
Well, what we have in mind would be a kind of aggregation of the information that could come from the control and data plane. It's true, to be honest, that we have yet debate on how to name that plane. At the beginning was some called learning plane, but with the same purpose of collecting information from control plane and data plane. Now we are moving to telemetry plane, but we have yet some doubts it would be the precise name. But the essential idea would be having a plane for managing and handling the data. And with that data, triggering actions later on that could be actions at control plane or data plane. So that would be the purpose. It's a kind of aggregator of information that could be used for feeding AI control loops.
Yeah. Telemetry gives some other meaning. So
yeah,
in this
great
case.
feedback. Diego, can you quickly speak?
Very fast. It's more a comment to what Marie-José was saying. when asking about this. Just a remark that, as Luis said, it was important that we're not trying to make a totally isolated, fixed layering approach, but the idea that the different layers can interact with one another. And precisely because of that, one of the ideas that we have in the QIRG, we are discussing a model of quantum networks based on previous experiences we have had with QKD, etc. And after some discussions with Luis, very likely we will go for trying to apply the same model and trying to portray how a quantum network would look like in this environment. Just as a note, I wanted to say it.
Thank you.
Thank you.
Thank you.
Thanks so much. Okay, our final presentation is about security. It's the individual draft. And let me bring that up. Hello, Pascal.
How much time?
Well, if you could fit this in 5 minutes, that would be ideal. Thank you. In fact, if you'd like, I can put a timer up on the screen so you can see.
Okay.
Yeah, there it is. Oh, and you have it there as well.
So just 2 words about Telecom Paris, because Telecom Paris is not a company. Telecom Paris is a university in part of Institut Polytechnique of Paris, and it's a place where 1 century ago was invented the world's telecommunication by Edouard Estomier, just to say we are not a company. So next slide. So the goal of this draft, is to, it's a tentative to define some security features about COIN. And so as it is mentioned in COIN draft, COIN works with programmable networks devices, that's to say device connected to network with some computing resources. And such infrastructures could be integrated in edge computing or 5G slicing. So a program works with several PNDs, exchanges in data over secure communication. So in that context, there is a need for security for intrinsic, that's to say, infrastructures, that's to say, COIN is an infrastructures, and such as it needs some security features. But the other part of which is contained in the definition is that programs are running in COM system. So it means because you run program in this environment, you also could need some security feature for the program itself. So next slide, please. So intrinsic COIN security, that's to say, infrastructure security. So COIN should rely on a fully encrypted communication. So if you do that, you need authentication and keying mechanism that could be based on asymmetric or asymmetric secret. And another important features maybe is about billing, because in communication, billing already exists. You have reduced server, for example, they provide billing features, but also in blockchain, when you use blockchain such as Ethereum with smart contracts and so on, you have something called the gas price. So it's mean when you talk about distributed computing, you may also think to billing features, how the service could be charged if you need to charge the services. So next slide, please. So this is an illustration of what could be infrastructure security. So because you are going, PND are going to manage key, they should need a key management system. And after, you could have 2 kinds of infrastructures. One should be centralized with something called the authentication center that will provide key through pre-share key. And this processor could also include secure physical identities such TE for trusted execution environment, or secure element. So next slide, please. So about program security, so you could have some security requirement. For example, if your program computes some transaction for the blockchain, you need to store a key somewhere. And for example, in another draft, we have something called Internet of Secure Element, which is the idea of putting multi-tenant security features in networks. Could be in PND, could be in authentication center, it could be in edge computing. And again, if you need computing fees, how can you evaluate this fee? So next slide, please. So identity, we need an identity for PND because from this identity knowledge, you should get information about the computing resources available in this PND and the trust level. Trust level is something very important because you need, when you delegate the computing to somebody, you need to know if if the program will be executed, let's say, in an honest way. So you have two kinds of architecture. You have single tenant. Let's say all the PND will be owned by the same entity, like in, let's say, in mobile networks, for example, all operators and all a set of communication features. And multi-tenant architectures mean you will have some cluster of PND that will be managed by several operators, in fact, or several owners. So next slide, please.
Okay, and just letting you know, you need to finish.
Two last slides.
Okay.
And so this is an example with using asymmetric architectures. So it's been you give a certificate to every PND, and for that you have a tenant which is a certification authority, and so a user that can be a PND, when you want to use a set of PND, he has a certificate, and so he may establish secure channel, and if you want to use two cluster of PND managed by different owners, then the user could have two certificates. And this is my last slide. Next, please.
Thank you.
And this is an example with symmetric architectures. So in symmetric,
and this is what you added to the draft between the last one and this one, for those who may not have looked at it.
Then it means you have an authentication center, and so every PND and user some relationship with the authentication center. And so if your user, which can be a PND, want to interact with a PND, he should require for the authentication center some token, ticket like in Kerberos, or token like web token, in order to establish secure communication and exchange some services. And again, if a user, if you want to use two kinds of PND managed by two management entity, then you should require this credential from several authentication centers. And that's it.
Great. Marie-José, you're in the queue. You're next.
Yes, I think it's interesting that your system doesn't have anything coming from the user. It's all coming from the network. And if I follow all your arrows, the only things that come from user are some kind of dash. I would say, from what I know, it should be the opposite. The user should be in charge.
I don't know who is the user of the system. It could be a PND. So,
well, it could be anything, but what I'm saying is that your architecture is very operator-centric, and for lack of time, maybe we can take that on the list, because this is an interesting thing, because from my world, this wouldn't work.
As I say, it's not operator, it's either single tenant or multi-tenant.
Well, your user is just a passive agent in this.
Yes, but
And I think the user should not be passive.
Yes, agree. But the user is a generic term. It doesn't mean that it is a user. It means that it's somebody that communicates.
Well, then maybe you can update. Maybe you can update your draft to make sure that we understand who the user is. But again, we're out of time, so.
But yeah, it would be great to have an update to clarify this, and also to take further questions and feedback to the list. Okay. Thank you very much. Marie-José, would you like to wrap up?
Yeah, I think we addressed everything. I think I'm very happy that the view of the 4-year is actually also shared by most of the people who presented today. I think I will take Colin's comments into action items to see what we can do to that. We always say we're going to have an interim, but we always have so much work going in parallel. But maybe, yes, maybe end of September we can think about it. And for Prague, I know we've had a request to not overlap with this conference on NFBSDN in Germany, but IETF.
We'll try.
Yeah, IETF scheduling is already complicated, so we may ask not to be on these days. But for people from that conference in Dresden, I think you can always listen to the recordings, and we're going to make our best to do this. So
people are starting to leave because of the deadline, so I think we should wrap up and thank everyone for staying with us, especially those of you in time zones where it's well after midnight. And
yes, especially for people from, I know China and is 12 hours ahead of me, which is like 2:32 a.m. Thank you so very much, Jeff, have been there.
Thank you for all the drafts and presentations, and especially for the discussion and comments. Let's continue on the mailing list. Thank you so much.
And yes, I can just say for all the other chairs, we're so happy we have you guys in our team, and we are moving forward. And I think this idea of computing in a network that started with a switch is now much more than that. Thank you so much, guys, for all the research.
Thanks, everyone. Bye-bye now.
Bye.
Oh my God. I always feel